Hi everyone, my name is Andrew. I'm a Spark committer at Databricks, and today I'll be talking about memory management in Spark. Now before I begin, I'd like to tell you up front that I do not have a demo prepared for this talk, unfortunately, but I promise I'll still make it as exciting as if it had one. So in this talk, I'll be covering a lot of internals in Spark. In particular, given a simple Spark program that looks something like this, we'll take a deep dive into all the cool things that go on behind the scenes. So what happens when the user does caching, how Spark manages that memory, the memory contention issues that might arise as a result of that, and once we take care of the memory contention issues, potential optimizations that we could do to make more efficient use of memory. The option to use off-heap caching and off-heap execution memory as well, and the performance benefits that entails, and really other potentially scary things to average Spark users. So you might be thinking to yourself, well, if I'm just an application developer, why do I care about all these internal details of how Spark manages its memory? Well, it turns out that not just in Spark, but in any data-intensive processing system out there, memory is an extremely indispensable resource. And I would even go further to say that efficient memory use is critical to good performance, that techniques for managing memory efficiently are commonly transferable across systems. So to illustrate what I mean by this, I'd like to borrow from an analogy by Jim Gray. So to summarize all the distracting graphics on the screen, essentially what he's trying to say is if you try to read something from memory, it's like going all the way to Sacramento, which takes about 90 minutes. Then reading the same thing from disk is like going all the way to Pluto, which is many orders of magnitude slower. Now the way this applies to Spark is that where possible, we try to keep as many things resident in memory as possible. And otherwise, we have to incur a heavy penalty of performing disk I/Os. So in an environment like Spark, for this reason, memory is always a constrained resource, because if you had more memory, then you would avoid spilling to disk as much. So unfortunately, because everyone wants memory, there's naturally going to be some memory contention issues that we need to address. And these issues have posed challenges for designing a sensible memory management system for a system like Spark. For example, there's memory contention between execution and storage, which are the two main usages of memory in Spark. In the next slide, I'll explain immediately what these mean. There's also memory contention across tasks running in parallel. And in Spark, a task is essentially the smallest unit of execution that represents a partition in your data set. Further, there's also memory contention even within a task across operators. I'll also dive into more detail about what this means exactly later, but for now you can think of an operator as a step in transforming your data. So for example, a sort or a group by. I mentioned earlier that there are two main usages of memory in Spark, and these are execution and storage. Execution is kind of like the memory that you use to buffer intermediate results as you perform your computation. For example, if you're doing a group by, you're going to need to put your values in some sort of hash map, and you need memory for building that hash map, so that's execution memory. Storage memory is perhaps more familiar to the user. It's basically so when the user caches their data set, what happens is we're going to put the values of that data set, put it in an array somewhere, and keep it in memory. So that's storage memory. The main difference between the two is that execution memory tends to be quite short-lived. As soon as you finish the computation and the results of that computation have all been consumed, then you can immediately go ahead and release your execution memory. However, for storage memory, the purpose is for future computations to be able to reuse that data. So we can't just remove it whenever we want. We have to essentially explicitly remove it or let LRU take care of it. So to illustrate this with an example, suppose I have an iterator of numbers. I want to sort them. So the sensible thing to do here would be to read all of those numbers into an array of some sort and run quicksort or some other sorting algorithms and output an iterator of sorted values. Then I might go ahead and run some action on it. For example, I might take the first 3 elements and so on. So the memory used for buffering the input data here is known as execution memory. Now, what happens if I want to get the sorted values again? Well, the contract of the iterator is that you can only traverse it once. So what this means is we're going to have to essentially perform the sort again to get those values. And this could be very expensive. So perhaps a better thing to do here would be to cache the sorted values if we know that we're going to reuse them over and over again. So now we can go ahead and run whatever actions we want without having to trigger the sort again. So the memory used for caching here is what I call storage memory, while the memory used for buffering the input data only to sort them is called execution memory. So here you'll notice that execution memory is rather short-lived because as soon as we consume the sorted values, we can go ahead and release it. We no longer need that memory anymore. So now that we understand what execution and storage are, let's address our first challenge, which is how to arbitrate memory between the two use cases. So the simple solution here is what I call static assignment. So suppose you have your total available memory here. For our purposes, you can think of this as on-heap memory, the size of your JVM. What this says is essentially assign a static chunk for execution and then assign a separate chunk for storage. So these are two completely distinct regions. They don't interact with each other in any way, and this is what I mean by static assignment. So this has been the solution, this had been the solution since Spark 1.0, which was released more than 2 years ago. And recently we changed this a little bit due to some problems that it has, which I'll talk about in it shortly. So let's run through an example of what this looks like in practice. So I'm going to acquire some execution memory. That's what the little green bars at the bottom mean. And then I'm also going to acquire some storage memory for caching some data set. So eventually, I'm going to run out of execution memory. So what happens now is that I'm just going to spill whatever I have in my execution memory pool to disk. Right? And as I mentioned before, this could be very expensive. Right? So let me go ahead and do that. And then similarly for storage, if I keep acquiring storage memory, I'm going to run out of storage memory, and I'm going to have to do the same. More specifically for storage, we're going to evict the least recently used block to disk. So in Spark, caching is expressed in terms of blocks, and each block is, you can think of it as an RDD partition, for example. So let me go ahead and do that. So I mentioned before that efficient memory use is critical to good performance. However, the inverse is also true, which is that inefficient memory use leads to bad performance. And in this case, the inefficiency is that execution has to spill to disk, even though there's all this available space on the storage side that we're not taking advantage of. So almost by definition, execution can only use a fraction of the memory, no matter what's going on the other side. So you might argue that, well, one way to solve this is to simply tell the user, have the user tell us how large each region should be. If the user knows that they're not going to use any storage memory, then we'll just go ahead and set that to 0 and give all the available memory to execution. However, this poses another problem, which is that efficient memory use now requires user tuning. Essentially, it bubbles up the complexity that we should handle internally in Spark to the user, and this is just not a friendly API, especially to newcomers to Spark. So let's fast forward to 2016. What are some things that we could have done a little better? Well, what about instead of expressing execution and storage in terms of two separate chunks, we express it in terms of one unified region, such that they both share. So as an example, what happens is if I try to acquire more execution memory, I might borrow from the storage space if there's not any storage memory being used. So previously in the other approach, I would have already spilled by now, but now I'm just happily acquiring execution memory without spilling. So this is what I mean by unified memory management. It has been in Spark since Spark 1.6, which was released earlier this year. So this is kind of a silly example, right? There's like nothing on the storage side. So what if there's already some storage? Okay, so I'm going to acquire some execution memory. I'm going to keep sorting and sorting, and eventually I'm going to run out of execution memory. And what happens now is I'm going to evict storage. So as before, I'm going to evict the least recently used block to disk. So once I do that, I might keep acquiring execution memory and evict more storage as I need. So what about the other way around when storage tries to acquire memory? So storage now is the one that's growing. I'm putting in a new block and another block, and eventually I run out of storage memory. So what happens now? Any guesses? Yeah, so it turns out that as before, we also evict storage memory. So the key thing to note here is that essentially what this is doing is to make space for the new block, we go ahead and kick out some old blocks, right? That's what the LRU is doing. So there are some design considerations here. You might have noticed that in both cases, we chose to evict storage rather than execution. This might be a little surprising to some of you, but the main reason behind this is because spilled execution data is always going to be read back from disk, whereas cache data may not. And what I mean by this is if you're spilling something while you do a sort, you're going to have to return those values to the caller. So either way, you're going to have to read them back from disk, and there's just like no getting around that. But anecdotally, I've seen many applications where the user just overly aggressively caches things. They put .cache after every single line. That doesn't do anything. At best, it just ruins your cache locality. So my point here is that it's a very real scenario where the cache data is never read again. You might have another concern where what if the application relies heavily on caching, such as like a machine learning application? So we can't just blow away all the cache data nonchalantly. So instead, the solution here is to simply allow the user to specify an amount of storage memory that cannot be evicted. So note that this is not a reservation. We do not pre-allocate a chunk of memory in advance such that execution cannot borrow from it. Rather, once there is already cache data, then this value comes into play. So let's move on to the next challenge where we try to solve memory contention across tasks running in parallel. So again, the simple solution here is static assignment. So suppose my worker machine has 4 cores. Essentially what this means is I will have 4 fixed slots, no matter how many tasks are actually currently running. So even if I have 1 task running, it's only going to get at most a quarter of the total memory. Perhaps a more efficient alternative is what I call dynamic assignment, where how much memory a task gets depends on the total number of running tasks. So if I'm the only task running, I can feel free to acquire all the available memory there is. However, as soon as another task comes in, I'm going to have to spill to disk and free space for the new task. And this is because we want to ensure fairness, which is important. So what we end up with essentially is something similar to what we had with static assignment, where we have 2 slots. However, the number of slots are determined dynamically based on the number of tasks. And the spill thresholds for each one of these tasks is now much smaller than before, and so on. If we have more tasks, we're going to evict existing tasks to make room for them. One notable change in behavior here is that if I have a straggler, which is a last remaining task that blocks computation. So these are potentially expensive because everyone else is already done, but you're the last one kind of chugging along. Ideally, you should get all the memory available, and that's what this model allows you, because the number of actively running tasks is now 1, so you can feel free to get all the memory you want. And this has been the solution since Spark 1.0. In these past 2 years, we haven't really noticed major problems with it. It seems to have been battle tested pretty well in production code, so we haven't found any reason to change it. So a simple comparison between the 2 models will quickly reveal more similarities than differences. In particular, both of them are fair and starvation-free. For the static case, you can easily see why it's fair. It's pretty much the definition of fair. Like, you literally can't get more fair than that. In the dynamic assignment case, it's also fair because it's basically the static assignment model, but the number of slots are determined dynamically, such that each actively running task gets the same amount of memory as everyone else. It goes without saying that the static assignment model is a little simpler, and however, it doesn't handle stragglers, which dynamic assignment, which is what Spark does. So now that we've handled memory contention across tasks running in parallel, let's address the memory contention across operators running within the same task. So due to time reasons, I'm going to sort of zip through this part a little bit because I have more stuff at the end that I want to talk about. So you can look at the slides afterwards. They'll be posted online. So suppose I want to run a simple query that looks something like the following. I want to do a group by and an order. So the resulting query plan is something that you see on the right. First, it'll do a scan, and then it'll do a project to filter some columns, and then aggregate and sort. So it's worth noting that all of this happens within one task. Right? So there's memory contention across the different operators. So to illustrate this, let's say my worker has 6 pages of memory. So a page here is essentially a fixed unit of memory. It doesn't really matter how much it actually is. So aggregate is going to grab all 6 pages, and then it's going to use those pages to build a hash map that looks something like this. And then when it comes to sort, it realizes that it actually can't acquire any memory, so it has no choice but to fail. So a simple solution here is to simply reserve a page in advance for each one of these memory-intensive operators. So in this case, we know sort and aggregate are both memory-intensive, so we're going to give them a page in advance. So this solves the starvation problem, but it's actually still not fair, right? Because if we go ahead and run through this, aggregate is just going to grab 5 pages, leaving sort with only 1. The bigger problem here is it's simply not feasible for some query plans. What if I have 7 operators that require memory? It's just not doable. So perhaps a better solution is what I call cooperative spilling. So it works like the following. Suppose aggregate grabs all 6 pages, and then when it comes to sort's turn, it's going to cooperatively force aggregate to spill a page. Right? So essentially, it steals a page of memory from aggregate, and then when it determines that it needs more pages, it's going to force aggregate to spill more pages, and so on. So here, they both end up with 3 pages, so it's fairer than the one before, and aggregate doesn't have to spill its remaining pages. So this has been the solution adopted since Spark 1.6. Oh, also, I'd like to mention that I didn't just talk about the first solution to make this solution look better. The first solution was actually a real approach that we actually thought of implementing in Spark until we realized later on that there are some problems. So these are both solutions that we've considered. Now, as a quick recap, I'd like to summarize the 3 major sources of contention that we saw, which is between execution and storage, between tasks running in parallel, and across operators running in the same task. Perhaps a common theme across all 3 of these is that it's generally a bad idea to statically reserve memory in advance, because that means someone's not going to get some memory even though the other guy's not really using it. Instead, a better way to deal with this is to force members to spill when there is memory contention. So essentially, we're solving memory contention lazily rather than eagerly. So now that we've dealt with the issues with memory contention, I'd like to talk about the optimizations that we can do. So you might have heard of this term, Project Tungsten, floating around. Essentially, the high-level goal is to rewrite the execution engine in such a way that is more aware of the lower-level constructs. For example, it introduces a very compact binary format to represent rows. And there are many advantages to that I'll talk about shortly. It also introduces data structures that are more aware of the L123 caches to improve the hit rates. And there's also code generation, but that is not really relevant to this talk, so I'm not going to talk about it. So perhaps the main motivation for Tungsten is that Java objects are very expensive. A simple string like ABCD actually takes 48 bytes for some reason, even though you can really encode it with just 4 bytes. It gets worse if you try to represent a row with Java objects. So here we have a simple schema, an integer and 2 strings. So we're going to go ahead and box all the primitives and introduce a bunch of objects and make the hash code really expensive. So with Tungsten, a better way to format the row would be in binary format, where we just pull the primitive types directly into the row, directly as bytes, because we know exactly how large those are. And then for variable length data, like strings, we can go ahead and store the offset, and then have it point to the length of the data and the actual data that follows. So the details here don't really matter. The takeaway here is that this compact storage format allows us to essentially reduce our memory footprint significantly, and that's one obvious advantage because now you can pack more rows into memory. Perhaps a less obvious advantage here is that it allows you to skip a lot of serialization and deserialization because the row is already serialized. And because you know exactly what the schema is, you also know the offsets, so you can operate directly on the serialized data. Another aspect of Tungsten is what I call cache-aware computation. So the high-level idea here is to lay out data in memory in such a way that is more conducive to a higher hit rate for your L1, 2, 3 caches. For example, if I want to sort a list of records, common and very sensible approach to doing that might be to put all the pointers in an array and sort those pointers instead of the actual records. However, this actually has pretty poor layout in terms of cache locality, because every time we want to do a comparison, we have to dereference 2 pointers, and that leads to a lot of random memory accesses. Instead, a better way to perhaps lay out the data is to sort at least part of the key along with the pointer, such that every time you do a comparison, you compare 2 things that are pretty near each other, probably much nearer than having to do a dereferencing. So this is just one of the many optimizations that Tungsten allows. There are many other ones that I'm not going to talk about. Finally, off-heap memory usage is another very important way to make use of memory efficiently. So this has been available for execution since Spark 1.6, and today I'm happy to announce that it will be available for caching as well in Spark 2.0. So a little bit of motivation as to why this is important. It's actually super important for large heaps. Suppose you have a heap of 256 gigabytes. What's going to end up happening is at some point you're going to see like GC storms. So you're going to see GC pauses that last for minutes, orders of minutes, and that's very bad. It's not only bad because like your executor is not doing anything while it's doing a GC pause. It's also bad because for a communication-intensive system like Spark, when you send a message, you expect the other guy to respond more or less quickly. But if it's stuck in a GC pause, then it might respond too late, and you might have timed out the connection, and that could stall progress quite significantly. There are also many other potential advantages. I'm not going to talk about all of them, but I would like to talk about dynamic allocation. So dynamic allocation is a feature in Spark that allows you to scale the size of your cluster up and down based on the workload. So for example, if you realize that you need more resources to do your computation, you're going to ask for more nodes. And then when you realize that your cluster is idle, you can go ahead and kill your executors. So how this applies to off-heap memory is that when you kill an executor, if it had cache data, then previously you would have just blown away all the cache data on that executor. But here, with off-heap memory, we decouple the concerns of the lifetime of a JVM and the lifetime of the cache data, such that you can reason about them separately. So if you kill an executor, the cache data is still going to be there. You can access them later. OK, so for more information, you can look at these other talks and the Jira. Oh, before I finish, I'd like to point everyone to Community Edition. It's like a very cool platform for you to try things out with Spark. Thank you very much.
Thanks very much to Andrew for this awesome presentation. We've got about 2 minutes left for questions, so if you do have any questions, please come to the center aisle. There's some microphones here, and by all means, ask away.
Can't believe I finished up.
That's actually pretty impressive, dude. Yeah. All right. See if anyone else? No?
Huh?
All right, cool. All right, well then, thanks very much. Oh, sorry. Go ahead, please.
How do
the first microphone here. Yes.
Oh, sorry. Yeah. Hi. We use PySpark extensively, and I would like to understand how I can better monitor the spawning and the memory usage of my Python workers. Right now, what I do is I just SSH into the worker, and I do top. And I have no way of knowing which part of my code the Python workers are corresponding to, and how their memory usage is related to the Python worker memory I set in Spark config. It's complete black box for me. Thank you.
So the question is, how do we monitor memory usage when we use PySpark? Unfortunately, the answer is there's currently not a great way. I'd probably do the top thing too if I were you. in the future, we might expose some of that memory information on the Spark UI. This is not really specific to Python, but like more generally, users can go to the Spark UI to understand more about the memory usage of their application. Yeah.
All right, thanks.
Not a great answer, I'm sorry.
All right, thanks.
So we only have time for one more question. So the person in the second, in the blue shirt in the second minute. We also have booth duty actually at the Databricks booth, so you can also ask questions there. Okay, so just as a quick call out. So for the person in the back, you're the last question.
Okay, so you're trading Java memory issues for poor malloc and scalability and fragmentation issues. How do you expect to deal with those instead?
That's a great question. So currently, we don't really have a great answer to that either. We manage the memory ourselves inside Spark. So yeah, actually, it just depends on whatever the underlying platform currently does.
Yeah.
So in the future, we might address that as well.
Yeah, they're terrible. So okay.
It's definitely a real concern, though.
All right, thanks very much, and we'll shift over to the next session in 5 minutes. Thanks a lot, everybody.